okay, and the different branches. And the first thing we did was a exclusive OR between the register and itself. So regardless of what the contents of the register are, is if you take the exclusive OR with the same thing, you get zeros, right? So this is clear. The zero flag gets set. This is what gets stored in REX. And since it's a non-negative number, the sign bit is 0 and so forth, and all is good. So then when we go to subtract 1 from that value, we'll get -1, which looks, all absolutely looks familiar. Okay, so it's no longer 0. There wasn't any overflow. It's now a negative number. And this was the one we had a question on the last time. So here, the way to think about this is that for unsigned arithmetic, there's a notion of a carry both carry out on like addition and a borrow on subtraction. Okay, so the fact that we had to borrow off the edge of 0 in order to have something to subtract 1 from meant that the carry, or I guess the carry borrow flag you could call it, is set to 1. Okay, and then we do this comparison instruction where we compared 2 to here, and as it says here, that's the impact. The effect of that is to take the context of REX and subtract off 2. Okay, and so you get -1 minus 2, so you get -3. Now, because it's the compare instruction and not actually a move, it doesn't alter the destination. So REX stays the same. Okay, but now we have the sign flag set and the sign condition flag, and all the rest turn to 0. And then we go and we do this test. So a set L is a less than comparison, and it's satisfied when the sign bit is set and not the overflow, or vice versa. In this case, that's true. Okay, and the set L instruction puts the result in AL, which is the lowest low order byte of REX. So you can see that's why there's a 0, 1 right here. Okay, but important property is that these instructions are for sort of taking advantage of the condition codes. They don't set the condition codes themselves. Therefore, none of the condition codes are changed. They're left as they were here. It's similar to, like I said, an LEA instruction doesn't affect the condition codes. So if you had an LEA instruction, say after this compare, the condition codes would remain what they were as a result of the compare. All right, and then we have this 0 byte extension instruction, which zeroes out all the remaining bytes. And again, it does not change the condition code. Okay. So any questions on that? Yes. AL is if you remember our register picture. So like if you have REX, then this lower half is EAX, and the lowest byte of that is A. No. Okay, so it's specific to REX. Did the AL what? The AL, I'm not exactly sure what your question is. The AL only overwrites this last byte. Okay, and then this instruction here moves basically what's there, the 0, 1, into EX, which is the low order bits here, and also zeros out the rest. So you get all these zeros here, and you get this byte that was there. Okay, any other questions? Yes?
What's that L to? What is that L?
So set L is shown here in this table. It's based on whether this condition is satisfied or not, the exclusive OR, the sign flag, and the overflow flag, it puts either a 0 for false or 1 for true in whatever the destination is. In this case, it's this AL. Okay, so that's why you see it overwrites just that one last byte of the RAX. Yes?
If you just put the result set L directly into RAX, will that zero out everything? So that's
No. It only overwrites the low order byte. So whatever's here, the rest of it is unchanged. Okay, good. Let's get all that. And return to our regular scheduled programming. Here we go. All right, so this is the third of 5 lectures on machine level programming. And we're going to talk today about procedures. Specifically, we're going to talk about the mechanisms, sort of the big picture mechanisms involved in procedures. If you've thought about languages like C, you have sort of a notion about how procedures work. This is going to look at what's going to happen at the assembly code level. Key component of this is going to be the stack. Okay, so we're going to talk about the structure of stack in the x86-64 architecture. We're going to talk about the various calling conventions, some of which we've seen in lectures so far, but here we're going to give sort of the overview of how it works all together. Passing control to procedures that are called, passing data, arguments, and so forth. Managing local data, that's data that the procedure you called is allocating. And then we'll look closely at recursion. All right, so if you kind of list all the things that need to happen in order to call a procedure, there's the notion of passing control. So you're flowing along in the program and suddenly see this procedure call. And so now you got to jump control to where that procedure starts. Okay, so that's the arrow shown in red. And then after that function, that procedure completes, you want to return back to right where you left off. Okay, so it's the very next instruction after the call, and so that's the arrow. In terms of data, there's the argument that get passed into the procedure, into the function, and that's shown with the arrow in blue. And then if it returns something, there's the return getting passed back to the original callee. There's memory management. So notice that this procedure allocates some local state, and we need to handle that carefully because, particularly in cases of recursion, this exact same procedure is going to be called again and again and again. And so you want a separate instantiation of this local state. Okay. So those are 3 components. They're all going to be done and we'll show how they're all done in machine instructions. Now, one thing to note is that not surprisingly, compiler writers try to use as few instructions as they can, and so any part of a general calling convention that's not needed, that can be shortcutted without affecting correctness, will be done. Okay, so the only parts that actually needed will be materialized. Okay, and this whole API that we're going to talk about is called the Application Binary Interface, or ABI, and it's just a convention. All right, stacks. So if this is our memory, the big long chunk of memory, then different segments of memory are going to be allocated for different purposes. Okay, there's going to be memory where the code resides. There's going to be memory where heap data, where globals reside, and so forth. But today we're going to talk about the stack. Okay. So if we look at the stack, we see that in the way we think about x86-64 stack, the top of the stack is actually down here, and the bottom is up here. Okay, and this arrow indicates that the top is the direction we go. So this is sort of this boundary here is once it's set up, it's fixed and basically stays there unless there's some issue where you run out of memory for your stack, then you have to relocate the whole stack. But, you know, in 99% of all your programs, that's not going to be an issue. There's plenty of space for your stack. And so that part will stay anchored, stay fixed. And what will happen is the top will jump up and down. Okay? An important register is the RSP, which points to the current top of the stack. Okay, so as I mentioned, the stack goes down. Okay, if you think about the address space, it's important to note that the addresses increase going up. Okay, so if you were to draw all of memory, you know, the 000 address would be way down here off the page, and you know, the maximum address would be way up here. Okay, and the reason that's important to know, the convention of the machine, is because that tells you whether you want to subtract from the stack pointer register or add to the stack pointer register. Okay. All right, so there are two instructions in x86 that are specific for stack, a push and a pop, as you can imagine. So a push instruction takes a register and it fetches the operand at that source, and I think I have an animation here. So if there's a value, if that, say it's a register or whatever it is, if there's a value in that register, it gets put where the stack gets advanced by one quad word, and the value gets placed there. Okay, so you fetch the value, you decrement the stack pointer by 8, so it went from here to here, and then you write the address at where the stack pointer now points. Okay, and the notion is that basically where the stack pointer points on this way is all in scope valid values for the executing code, and everything on this side of it is garbage. Okay, not to be used without serious correctness concerns. All right, the opposite of push is to pop. So let's suppose that we have this value here on the stack, and it's a top. If you call the pop instruction, then it takes that value. The value is there, and increments the stack pointer by 8. And so again, because there are increasing addresses, incrementing will push it this way. Okay, so it pushes it that way, and then that's effectively saying now the stack pointer points here, and the top of the stack is now here. Okay. All right, and that destination the value is put in the destination, which is typically a register. Okay. All right. So notice that as I mentioned, the stack pointer changes, but you didn't, this stuff in here is left alone. Okay, it's viewed as garbage, but it's still there. Okay, and so this is a something to be watchful for when you're programming. It's also something that can be used in attacks against the machine if you're not careful. Okay. All right. So that's talking about the stack. All right. So we're going to go through the assembly code for some very simple functions, and this will be one of them. We'll go through this in some detail. So we have this procedure, this function molt_store, that takes 3 arguments and calls molt2. And here's molt2. Okay, and molt2 takes its 2 arguments, multiplies and returns the result. And then molt_store stores that result in the destination, the point at the address pointing passed to it. Okay, and what this gets translated into is these 6 instructions for molt_store and these 3 instructions for molt. Okay, and we'll, if you haven't seen this before, it's kind of a mystery. We're pushing something, we're doing this move, and we do the call, then another move, and then a pop here and here. We've got, there's our multiply and return and so forth. And what makes this all low overhead is the conventions about how the registers are used to pass the arguments and to return the results. So for instance, as we've seen in previous classes, RAX is used to store the result. So that's why when you pop back out of it, you know that the value that returned from this call, from this procedure, is in RAX. Okay? And similarly, by our convention that the first argument is always in RDI, and the second argument is always in RSI, the third integer argument is always in RDX. You can see that here's your RDX getting used here. You can see there's this shortcut here where because X and Y are actually passed in the proper order for A and B, they're already in RDI and RSI for mul2, so we don't have to put them there. Okay, so that's why there's very little going on before we make the call, and then the stuff is where we want it, RDI and RSI, and so forth. Okay, so that's the kind of thing we're going to talk about today, and we'll do it in one step at a time. Okay, so the first thing, of course, is that we talked about is the control flow. So here, the call instruction now, symbolically it's mul2, but once the code is loaded, there's some address in memory. In this case, it's this address here, where mul2, the code for that resides. Okay, so the non-symbolic version of this routine says, I want to do a call, and this is where the function starts, that exact address. Okay. All right, so in our current state, before we make that call, or we're about to make the call, remember RIP is the instruction pointer. So this says the program is currently executing the instruction at this address, or is about to execute the instruction at this address. That's right here. Okay, and stack pointer is pointing to 0x12, so it's pointing to the bottom element right there. Okay. So we're all set up, ready to go. Then what happens? Well, what do we want to happen? So what we want to happen is we want to take this value here, which is where we're trying to jump to, and put it in here, right? So that's where we want to go. So this, after we're done, should point here. Okay. And we also need for some way to get back. And the convention on how to get back is that you put the return address, where to come back to, you push that onto the top of the stack. Okay? So after we're done with this procedure call, the next instruction we want to execute is this one right here. And so therefore we want to put 400549 here. Okay? We want this to now point to here. And that's basically what this is showing, okay? That the stack pointer now points here as opposed to up here. This new item we just pushed on the stack points to where we're going to return back to after the procedure's done. And the instruction pointer points to the start of this function. Okay? Questions on that? Yeah?
Is the instruction pointer only going to be 400560? Or is it just for that one?
It's that one function. So wherever the function bolt2 happen to be placed in memory. All right, so now we chug along through this procedure and we get to the end. Okay, what do we want to do now? Well, we see this return. This return says go from where you are now to whatever the return address is, which is this guy right here. So look at the stack pointer and find this return address, and that's where I want you to jump to. Okay, so that's what happens. The instruction pointer now points to where we wanted it to go, which is the instruction after the call, and this is back to being at x120. Okay. Any questions on that? Yeah.
So
the return address, yeah, goes in the same stack as everything else. Okay, and again, that's a potential weakness for attacks that you'll see when we get to attack lab and things like that. Right? Yeah. This question.
Is RBX a pointer to the stack where the return is stored?
The RBX? Not necessarily, no. So here we're in a case where RSP was pointing to the return address. The stack pointer, the return address was the top of the stack. We'll see more general examples. Maybe you're thinking of R, or maybe I misheard you. You're thinking of RBP? Is that what you said? We'll get there. So on that first example, yeah. So there's no RBX. Oh, I see. Here. Sorry. So it turns out that RBX is where we stored that had to do with the function itself. Turned out where we stored the address of where we wanted to put things was in RBX. Okay. So what this address was, we stored in RBX so that when we returned, we would take the return value and store it at that address. So that's happening here. Okay, sorry, I hadn't realized that RBX was on the slide. Okay, so the big picture about arguments looks like this. Basically, the first 6 arguments, we've seen this case several times. We saw this case today. After that, it goes to RCX, R8, and R9. And then it's like we said, the return address of AX. So if you have more than 6 arguments, then and only then do you start 6 integer arguments. You start placing them on the stack. So if there's a 7th and 8th argument, you up to n, you place them on the stack. Okay, so that's much less efficient, but most procedures have 6 or fewer arguments, so we're good. Yes. What exactly what? It's just a chunk of memory. So somewhere in the address space of memory, starting from address 000 up to the maximum address, there are regions of memory for things like code, like program code, for library code, for memory the operating system uses. There's heap, memory for the heap, which we'll talk about in another lecture. And there's also memory for stacks. Okay, and so it's just from where the bottom of the stack, and it grows down from there. Okay, good. Okay, so these are our procedures again. Here's mult store. Here's mult 2. And again, the convention is that the first argument is in RDI, the second one in RSI, the destination is in RDX. And when you get back, the return value is in RAX. Okay? So, so one thing you'll notice here is that, and then similar to that, we know that these are passed here and this is passed back here. Okay, so, all right. So one thing you'll notice here is that we had this RDX, and we're about to do this call, and there was concern that this procedure we're calling may actually need RDX itself, right? Maybe it calls something with three arguments, and so it needs RDX itself. So to make sure that this value that we're going to need when we get back isn't trampled on, we store it in another register, RBX, so that when we get back from this call, it's safe and hasn't changed. Okay. All right, so, and we'll talk about the conventions. Different registers have different conventions. We know, based on the convention around RBX, that it doesn't get trampled by anything we call. All right. Okay, so as I mentioned, we want to be able to support recursion. Okay, so we want to fire functions that define some local variables inside them, and we want every time we call that function, we want to make sure it's its own piece of memory, right? So if it calls itself recursively, it's separate allocations. Okay, and again, we're going to do that on the stack. There's a notion of a stack frame, which is just, if we've got our stack running down and we're, currently here with our stack pointer, and we stick the return address in here, and now we're getting ready to call another function. It's going to have some space on the stack for the stuff it's doing, okay, and that's called a frame, okay. All right, and so local variables and such will get populated in this area, and then including if it tries to call things and so forth. But then what happens is that when this function returns, we just get rid of the whole frame by just moving the stack pointer back to where it was. So if the stack pointer is here and we return from this, it pops back way up to here, okay? And then we can throw another frame on here and so forth. And we'll show an animation of that in a second. Okay, so let's suppose we have the following routines. Call chain example. We have a function u that calls who, and who makes two calls of AMI, and AMI is actually recursive. It calls itself, okay? All right, so what's it going to look like? Okay, so an example might be, u calls who, which calls AMI, recursively calls AMI twice, and then stops, and you come back up and you get the second call of AMI, and then you stop. All right, so we've got this notion of a frame. So this is the previous frame, and here's the frame for the procedure we're dealing with now. And it's going to contain local storage, return information, temporary storage as needed. Okay, and you're going to set it up. There's going to be some setup involved in terms of pushing arguments beyond argument 6, like argument 7 and 8, onto this frame. Then you'll do the call, and then when you're finished, it all unravel. Okay, we'll show an example here. So we're in U, okay, and now it gets to the point where it calls who, and so now we have the frame for who, and the stack pointer is always to the top of the stack here. Now there's this there's another register, which is RBP, which points to the sort of the other end of this frame, okay, and that register is optional because if it's typically only needed when there's a variable amount of stuff that's going to be put in here. Okay, if the compiler can't tell how much stuff you're going to put in here, then in order to find this return address that's going to need to jump back to U, it needs to know where this frame started. Okay, so if I'm here and I put the return address here, and now I call who and blah 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 blah, and I get to the end and now I'm ready to return. Well, I need to jump back to this place here. Okay, so I want to take whatever the current stack pointer is, and I want to move it back to here. If the compiler knows exactly how big this frame is, it's just simple arithmetic, right? I know I've put 8 bytes of stuff on there, or 32 bytes of stuff on there, so I just want to subtract off 32, and I know exactly what it is. It's primarily in the cases where there's a variable amount of stuff that gets put on here, that first what it will do is it will jump back to this, it will reference this base pointer to find out where it needs to revert the stack pointer to. Okay, but again, that's typically we won't see it because it's optional. All right, then who calls AMI, and you push that on the stack, and AMI is recursively calls itself, and AMI calls itself again. Okay, and so again, if there's local variables defined in AMI, you've got distinct copies of it in each of these recursive calls. Okay, yes?
So, assuming we need RVP for MI, how does it keep the RVP for the previous version of MI in memory? Does it have it as like sufficient amount of stack whenever calling the next MI, or?
Exactly. So if you need RVP, if you're going to be using RVP more than once, then you want to squirrel it away on the stack. So you can right. You need, like, after you're done with this one, you need the RVP for this one up here, right? And so the place to put that is on the stack itself as well. So you squirrel it away somewhere here so you can find it and then restore it. Yeah.
You said that RBX will like never change when returning from a function call?
So we're going to talk about that. We'll talk about the conventions on registers towards the end of class. So you can hold off your question until then if it's not clear the next game. Yeah.
What does RBP stand for?
Base pointer. The BP.
Just like the base of the frame.
Yeah. Okay, so then let's suppose there's no more recursive calls of AMI. So you just pop this off and move RBPI and pop again, and now we get to the second call of MI, and so you just push it back on, and you're done with that, and you're done with that, and then you're done. Okay? Okay, so let's look at a little bit more detail what's inside a frame. Okay, and again, in very simple cases, there's almost nothing. Like an example at the beginning of the class, basically we had a return address, and that was pretty much it. Right? There was no need for any of this other stuff because everything got passed in registers, so we were happy, and there were no local variables. Okay, so but the general case is that you have all the arguments beyond this the sixth one. Any local variables that need to be defined, and then this notion of any registers that you need to squirrel away so that they don't get trampled on. We'll talk about that towards the end of class. And then, as with the earlier question, you have the old value of RVP. If you're using RVP, then you want to squirrel away the old value of that. Okay, so we have the return address, which is considered part of the caller frame. And then the callee, which is what's getting called, has all this stuff. Okay. Did I cover all this? Yes. Okay, good. So any questions on that? Good. All right, so let's look at another example. So this example, you've got two arguments, and you're going to basically fetch the value in P and add it to this quantity val, and then store the result back in P. So basically, whatever's stored at location P is going to be incremented by the value of val. Okay. So what does the setup looking like in assembly code? Well, again, so RDI, RSI, right? So RDI, so you're saying I'm going to move. Fetch what's in RDI and store it in REX. Okay, so now X, whatever this X here is now in REX. Then I want to add that value to RSI, which is the second argument. So that's taking X plus val. Okay, and then I'm actually trampling on RSI and putting the result in RSI. Then I'm going to take move from RSI, basically do the store, and store through the address again, okay? So it's just load in the address, do the add, and store back, okay, and return. All right, so this is a very simple case. There was no local variables to worry about because we managed to get everything in registers. Okay, so even though the code shows local variables, there's nothing to allocate on the stack because we managed to get it all in registers. Okay, so very efficient, right? Very efficient call return. All right, so let's look at something that calls that procedure. So let's suppose that we have, 15,213, and for some unknown reason, we want to add 3,000 to that. Okay. And then once we've done that, then we actually want to sum those two numbers together. Okay, so what do we do? So the first thing we want to do is we want to move the stack pointer. Okay, well, we put the return address, and we're going to move this value onto the stack. Okay, and then in particular, we're going to move it 8 plus the stack pointer. So it's kind of first we subtract from the stack pointer, so we move it in one fell swoop from here to here, right, from here to here, and then we do arithmetic based on additions off the stack pointer. So instead of like a series of push, 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 where the stack pointer keeps moving, we just jump the stack pointer to a place that's useful, and then we do relative addressing off of that. So then we're going to move our 3000 into RSI, and now and we're going to put the address that we want to pass to increment. Remember, increment takes an address and a value. We're going to use LEA for actually what it's intended for, right? To load effective address. Put that in the register. Then we do our call, and then when we get back, we now have the result of the increment is in REX from the call, and this thing here, this 213, is we squirreled away on the stack, so we have it there, and so now we add it. Okay, and then we return the stack point. All right, so I think there's a little bit of animation on this. So so in order to get ready for these two arguments, again, we put the one argument in. So again, it's in RSI, but since this is a small value, it fits in 32 bits. We use the smaller form where we move only a long 32-bit quantity into ESI. So again, like the other registers, you've got RSI is the whole thing, and ESI is the bottom part. Okay, and then we load the effective address. So now we're good to go. Okay. That's said, and I already mentioned that. Okay. Okay. So now we do this call. Okay. And when we get back, we know that REX holds our return value. Okay. And so we're going to add. So that's this part. We're going to add in what we squirreled away on the stack. And you can see our answer. So now we know why we added 3000 to 15213. And then we have this weird thing that doesn't make any sense in terms of course numbers, that we add those two things together. Okay. And reset this stack pointer to where it was. Okay. All right, any questions on that? Yes?
So why should we subtract RSI by 16 only like 8 bytes?
So because we're dealing with a 64-bit, so in this particular example, it's not clear why the compiler did this. The codes that are showed in these slides are actual codes you would get like on the Shark machines, right? So my guess is that it was for some sort of alignment issue that basically wanted to align the stack pointer at 16, or if this had if there had been a return address or something, like if this function called something else, you would have had a space for it. I don't have a good answer for that, but for some reason that's what the compiler does. A lot of times it's either for alignment purposes or just in preparation for possible other uses. That's a good question, though. Okay. All right, so now let's get to the register saving conventions. Okay. So again, we have the notion of a caller and a callee. Okay. And we have these registers that they both want to use. So, so here's like a bad example. Suppose we had moved, 15.213 into RDX, and then expected to be there when we got back, but for whatever reason, this function procedure we called also used RDX. So it would trample over what we wrote before, and we would get the wrong answer. Okay. So we need some sort of convention, some sort of agreement. And so there's two choices, right? One is that if I'm about to call a function, if the caller wants some registers when it gets back, it should do the work of setting those values aside in some place that knows the callee is not going to, and all its descendants aren't going to trample. The other option is that the one you're calling, like if I call the function foo, and foo's going to trample on some register, it better make sure that it saves the old value and restores it before it returns. Okay, and that's the difference between caller saves and callee saves. Okay, so again, it's just a convention, okay, so we talked about this, the return value, the arguments, and then there's a couple of caller saves temporaries. So register 10 and register 11. If you want those values when you get back from the procedure, the caller has to squirrel them away on the stack and then restore them. Okay. Okay. Similarly, for all these guys, if I have something in REX, I'm about to call a procedure, call that procedure, or one of its descendants is likely to trample on REX. So I have to, as the caller, save this, right? And similarly, the function I'm calling may have arguments, and it wants to use these registers. It may call other functions that have arguments. So this is also caller saved. So all of these registers here, if you want their values, maintained across the call, then the caller has to squirrel them away on the stack and restore them when it gets back. Okay, or squirrel them away somewhere else. And that somewhere else can be these callee save registers. Okay, so callee save registers are registers that as the caller, I don't have to worry about. I could just leave stuff in there, and it's the callee's responsibility to restore them to their old values. So we had that earlier example of RBX. The reason that RBX was chosen, as opposed to say squirreling away something on the stack, which is the other option, is that if the callee tramples on RBX, it's got to first save the old value and then restore it. So from the caller's perspective, all these registers are unchanged. Okay. Okay, and the stack pointer is sort of a special case of this, right? So we know that when you pop back on the stack, and it's kind of where you left it. Okay, so it doesn't. Yeah. Okay, good. Okay. Any questions about before the quiz? Yes.
Why can't the compiler just point it on the registers instead of having
Instead of having.
instead of having like 2 set assignments to one and 4 set assignments to another, why can't the compiler just like point it off?
Well, you need a convention because if you remember, functions can be compiled separately, right? And so the compiler may not have the full picture of what's going on. The runtime can link in libraries that you didn't write, or the compiler had no control over whatsoever. So you need a convention that works globally, right? That all architectures conform to, so that you can do it when you don't have information about the other side. You're right. If you had perfect information, you could cheat, right? You could break this convention. But the general case, you don't have perfect information. It's just usually considered good practice to stick to this convention. Yes.
If the caller saves
So these are caller saved. So if I care about the values of R10 and R11, I should I should squirrel them away either in callee save registers or on the stack. Right? Because there's no guarantee that any of these are going to be the same as they were when I get back. So if I care about the value, I better stick it somewhere. So I
I'm saying like if you call like multiply and it puts two things like R10 or R11 and multiply happens to call add, like there's no guarantee that add can also use R10 or R11 to keep track of previous variables.
right. So you call if you call multiply, and then when you return from multiply. I mean, if they're still squirreled away on your stack, for instance, you still got them saved, and so when you call add can trample them as well. You don't care. If multiply calls add, again, multiply has got to save these contents of these registers since the caller saved before it calls add, and so it all just sort of works out, right? That basically, yeah. All right. So let's do the quiz. Canvas time. Yes. Stack point would be. Yeah, you should move the stack pointer first and then. Yeah, it's just a convention that's, because you want to be able to say that everything from the stack pointer, at all times, everything from the stack pointer, up is valid. It's within scope. All right, so I think people did pretty well in this quiz. Last I checked, personnel is not coming up. Okay, good. All right, so run GDB, good. Right, first 6 arguments stored in registers. Okay, and right, so only for the last one is only for the callee save registers that the function can assume the value is preserved across the call, right? The caller ones, they can allowed to be trampled. It's fair game. Okay, any questions on the quiz? Okay, all right, so in this example we have this procedure add 10 which has 10 arguments. And so where are those arguments passed? If we look at our cheat sheet of the registers, they're passed in the first 6 are passed in registers and the rest on the stack. Okay, and so we call that, and now where are these registers? Well, if you look at this, what it does is it adds the first 5 of them. So the first 5 here are still where they were. Okay. And so the question is, which registers do we need to save? Okay, any ideas? Well, it depends on what the compiler ends up doing. Okay, so basically, after making this call on the first 5 arguments, it's got a setup for the second 5 arguments. Okay, and which means that it's going to have to do some shuffling of the arguments, right? So basically, right, you want because they're not in the right place, right? So this 1, 2, 3, 4, 5. So R9, for instance, is where A5 is, right? So we've got to be able to move that into RDI and so forth, right? So it's kind of an interesting example, and I'm not going to dwell on it, but you can look at it later, because they all come in registers, and the first 5 are perfectly placed, but the next 5 aren't. And because of that, we're going to have to shuffle them into the right registers, and because of that, we're going to have to, to squirrel away some of the values so they don't get trampled when we do that. All right, and you can take a look at the code later. Although I will point out one thing. So remember how I said that you push the stack pointer, and then you reference things up off the stack. So you can see we have 24 off the stack, 32, 40, and 48 for these different things that are being scored away. Okay, so you decrement a large amount, and then you do reference it positive. So you'll see a lot of that in your code. Okay. Okay, so we have this x, right? And we're going to need it when we get back. But it's currently an RDI, and RDI is going to be used for the first argument here. Okay? And this is one of the okay, so what's going to happen is that we're going to push RBX, and then do all this. Okay, so we're going to want to squirrel away this value of x in RBX. But since RBX is a callee save register, this function has to squirrel it away here and restore it at the end. Okay, so from the perspective of this function being called, it's responsible for the callee save registers. So it's responsible for RBX. So that's why you see that. And so then it's safe to trample it internally and do all the stuff it did before. Okay, so that's what happens. You do the stack pointer, it gets saved here. Now you're going to subtract 16 off the stack pointer as we showed before. Okay. All right, and we move that there. I think we sort of already walked through this. Okay, we're going to return the result in RAX, and then add 16 to get the stack pointer back there. Okay, now we can restore the squirreled away value of RBX into RBX, and then we are ready to return. Okay. All right. Kind of went through that a little quickly, but I went through it slowly at the beginning when I first introduced the example. But is that too fast? Was there questions on that? Yes.
So when you went over solar, there were ASCII, RDX, and RAX, but it was like A plus RDX to RAX, or something of the sort. Is it different now?
You're saying that the code here is different from the code I had earlier?
I think before, where we were, why are we adding to RAX after the cost increment? Why wouldn't RAX just add a return value? And then I think the code was different, I think it was 8 plus.
So we return from Anchor, and the value of V2 is in RAX. So we have the value of V2 in RAX. But this Anchor 2 wants to return the sum of X and V2. So before we had to code for Anchor, this is like Anchor 2. It does that and then it does the addition. And so that's why we want to add the RBX onto what we got returned. Okay. So the X came in, we saved the register, we squirreled away the value of X in this register RBX. Then we knew it was there, and so when this value returned from Anchor, we added the two together to get the desired return value. This additional add here is because of this add right here. Other questions? Okay, so yeah, it's just showing the before the pop and after the pop of the restored RBX, restored whatever the original value of RBX into the register RBX. Okay, so let's look at what happens in recursion. So for recursion, we're going to use this example of a pop count that's done recursively. So if we're at 0, then we return 0. Else we take the AND, so we basically grab the last bit, the least significant bit, and add that to the pop count of the rest. Okay, so we shift off that bit and we recursively call pop count. And so again, if this last bit is a 0, then the pop count doesn't increase. If it's a 1, then the pop count increases. And so as we go through, we will count up the number of ones. Okay. So this is what the code ends up looking like. All right, so we start off by saying, well, if we're going to return out of this thing, we're going to want a 0 to return, so let's go ahead and do that. And now we're going to do this test. And so again, we do the test instruction, which, do you remember what that does? It takes its two arguments and does what to them? Ands them, okay? So that's just going to return the thing again. And so basically you just want to know whether this value in RDI is 0 or not, okay? If it is 0, then the JE condition is satisfied, and we will jump out of the loop and return when we're done. Okay? On the other hand, if it's not 0, then we're going to do save RBX. And we're going to move the current value of X into RBX. Then we're going to do this AND, right? We're going to AND 1 with EBX. And again, it's a little bit tricky because they're doing the shorter forms of things, right? This is equivalent to an AND quad of 1 in RBX. But since they don't need to use all 64 bits, they use the shorter form. Then you've got your shift right, which is this here. And then recursive call based on the now shifted argument. When you return, we have we have the value that gets returned, and we have the value that we squirrel away, and so we add those two together, and then we restore what was in RBX, and then, all right, then we return. Okay? All right, so again, this is the terminal case. It just uses those instructions there, the ones shown in red. Otherwise, we save our RBX. I guess I've just gone through the animation as I was talking about this. And then we've got the two halves of this. We've got the AND part and the shift part. We've got the recursive call. And then we've got this addition here that I mentioned. And then we restore RBX and return. Questions on that? Yes?
Like, why didn't we just move the RDI to a random color, save the register, but instead we move it to RDX, and we have to do the push and copy stuff in the console.
So the RDI here, for instance, this is recursive, so we're going to keep calling this thing, and it's going to keep. So we put it in here, which is a call eSave register, right? So that means it'll be. We're convinced we're guaranteed that its value will be maintained across the call. Okay. And so that's kind of what happens in every recursive call. If we were to put it in, the other place we could stick it is on the stack, and then it would just be at different places on the stack, and then we cover it from there. I'm not.
But actually, you can put it in random, in the color save the registers like R8, and you do that again, or
Well, if I put it in a caller save register, then I have to save it or it will be trampled, right? I mean, if I put it in some register that's caller saved, and in fact it will be trampled because when I do a recursive call, it will try to stick it in another register, right? I mean, this is the entire segment of code for every time this procedure gets called. So it's not like I have multiple copies of this procedure, and each one I can sort of select a different register to squirrel things away in. This is whatever choice I make here is the choice that all invocations of this make. Right, so it's going to trample on itself if I use a caller save. Right.
yeah, but I mean, before you recurse in this code, you should have to put the R8 into the stack as a caller, and when it's calling, you can use the R8.
I mean, the value that's being put here has changed every time because it's a different argument, right? There's not like it's a value to squirrel away once and they can all refer to it. It's a different value every time, so you need a different location for it. We can talk more offline. Maybe I'm not understanding the question. Okay. Other questions? Yes.
Sorry, so I understand where EBX is. If you move RDI to RBX, you can more EBX.
Yeah, so again, it's this weird thing where if this is RBX, the 64-bit of it, version of it, then EBX is the lower to half of it. Yeah, it takes some getting used to. Okay, so the nice thing about recursion is that we didn't have to really do anything different, right? It was basically the same mechanisms that we use for non-recursive procedure calls we use for recursive procedure calls, right? The stack frame ensures that we have private storage, so we didn't have to do anything fancy for that. The saving convention, whether it's caller or callee, makes sure that you don't trample on each other's registers and so forth. The stack discipline works just fine. If P calls Q, then you know that Q has to return before P can be done. And so it's this sort of this perfect last in, first out. It also works for mutual recursion, right? So if P recursively calls Q, which recursively calls P, which recursively calls Q, which calls P, and so forth, that's fine. The frames just pile up. Everything works beautifully. Nothing special has to be done. Okay. Okay, so important thing is that you have the notion of a stack. At any point in time, there's the notion of the frame that the caller has, right? And the last entry of that is always the return address. Okay, and then there's the part that the callee has, which can include the arguments that the caller places on behalf of the callee, right? Plus local variables that get allocated, plus any push and popping, squirreling away of registers that you need to do can occur in this, and that's frame, and then unroll frame, unroll frame, unroll frame. Good. So it's basically these conventions about the register usage, about calling and caller saves, that enables the whole code infrastructure to work and be efficient. And but it was all just conventions, right? I mean, why 6 registers? Why are these ones caller saves and why are these ones caller saves? There was some logic behind them, but again, it comes down to just policy, and a policy that was established and gets enforced. And that's it. Any other questions? All right, so next lecture we'll talk about data. How do structures get laid out in memory?